Okay, so we want to find the eigenvalues. So we need to find the determinant of 3 minus lambda, minus 1, minus 1, 0, 2 minus lambda, 0, 2 minus 2, minus lambda. And so the determinant will be 3 minus lambda times 2 minus lambda times minus lambda. So we can just write that as lambda times lambda minus 2. Then it'll be plus 1 times the determinant formed by the outer two columns, but that determinant is 0. And then it's going to be minus 1 times the determinant formed by those two columns. And that determinant is minus 2 times 2 minus lambda. So including the minus 1 there, this is just going to be plus 2 times 2 minus lambda. Or really, I guess I want it to be a negative. So I can factor out a 2 minus lambda. So I can factor out a 2 minus lambda, or lambda minus 2 is what I'm going to do. Factor out a lambda minus 2, and then I'm left with lambda squared minus lambda squared plus 3 lambda minus 2. Or this is lambda minus 2, factor out a minus sign, lambda minus 2 times lambda squared minus 3 lambda plus 2, or this is minus lambda minus 2. So this looks like it's lambda minus 1, lambda minus 2. Okay, so the eigenvalues are then 1 and 2. The eigenvalues are 1 and 2. The algebraic multiplicity of the eigenvalue 2 is going to be 2 because it is a double root of this characteristic polynomial. So the algebraic multiplicity 2. Okay, and so now we want to find an eigenspace. Now we want to find an eigenspace or a basis for the eigenspace E2. So in other words, we need to find a basis for the eigenvectors associated to 2. So in other words, we need to set lambda equals 2 and find the null space of 3 minus 2, minus 1, minus 1, 0, 2 minus lambda, 2 minus 2, 0, 2 minus 2, minus 2, or this is equal to 1, minus 1, minus 1, 0, 0, 0, 2, minus 2, minus 2. Okay, well, following the algorithm in the notes, we would swap the second and third row. But notice that if we do row 3 equals row 3 minus 2 row 2, that's also going to be a 0. So when we row reduce, this is 1, minus 1, minus 1, 0, 0, 0, 0, 0, 0. So x2 and x3 are the free variables. So the null space is given by x1, x2, x3. We'll say x2 is s and x2 is t. And the top equation says x1 is equal to x2 plus s3. In other words, s plus t. And so this is equal to s times 1, 1, 0 plus t times 1, 0, 1. Okay, so 1, 1, 0, 1, 0, 1, this is a basis. Okay, notice it could be that if you row reduce things a little bit differently, you might get two different vectors. So one way to do this would just be to notice two things. So I guess what I'm trying to say here is I'm not sure where this mark came from. What I'm trying to say here is that if you got a different basis, it doesn't necessarily mean that your answer is wrong. The basis you got could be the same as this basis, just written differently. So for example, if you look at the vectors 2, 1, 1 and 1, 0, 1, well, 2, 1, 1 is just these two vectors added together. So this is definitely going to be an eigenvector associated with 2. And then this is just the vector 1, 0, 1. So that's an eigenvector associated with 2. So these are both in the set E2, in the vector space E2. And they're linearly independent, and there's two of them. So this is also going to be a basis for E2. So don't be so alarmed if you don't get the exact same answer right here. It could just be that you row reduce things differently. And then you're going to have to make sure to see which one of these matches up with your answer choice. Okay, and let me see if there's a problem, a next part of this. Okay, So that's all I'm going to do for this problem, or for these 3 problems in this video.